In today's lecture, we're going to finish up chapter 25, covering the last couple sections, talking about dielectrics and Gauss's law. All right, so going back to dielectrics, look at it in an atomic view, where we're just looking at the molecules or the atoms of the dielectric. So there's two different types of dielectrics. There's polar dielectrics, which you have the molecules of some dielectrics, like water, have permanent electric dipole moments. All right, so when you have polar dielectrics, you have these permanent dipole moments created by the geometry of the atoms in the molecules. So in such materials, called polar dielectrics, the electric dipoles tend to line up with an external electric field. Since the molecules are continuously jostling each other as a result of their random thermal motion, this alignment is not complete, but it becomes more complete as the magnitude of the applied electric field is increased. So you have the alignment to the electric field is going to increase as the applied electric field increases. Or as the temperature and thus the jostling decreases, right? So if you lower the temperature, it's also going to help align the molecules. So this alignment of the electric dipoles produces an electric field that is directly opposite the applied field and is smaller in magnitude. All right, so you're going to basically develop this electric field that is directed opposite of the applied field, right? Because of the alignment of the dipoles. Now, you also have nonpolar dielectrics. So regardless of whether they have permanent electric dipole moments or not, the molecules acquire dipole moments by induction when placed in an external electric field. So this occurs because the external field tends to stretch the molecules, slightly separating the centers of the negative and positive charge. And we saw that in the previous chapter, where the electrons kind of get pushed, and then the protons will get pulled, or vice versa, and you create this sort of temporary dipole. Okay, so Gauss's law. What we have here is a parallel plate capacitor, and in A it's showing you without the dielectric, and in B they're showing you with the dielectric inserted. Now the charge Q on the plates is assumed to be the same for both cases. Alright, and that's shown here, the charge Q on each of the plates. So for the situation without the dielectric, the electric field between the plates can be found using Gauss's law. And we enclose the charge Q on the top plate with a Gaussian surface, and then applying Gauss's law, if E naught represents the magnitude of the electric field, we have that. So we can just say epsilon naught is equal to the integral of E dot dA. Oops. So that's just going to equal epsilon naught EA is equal to Q. Therefore, if we again use E naught to represent the magnitude of the electric field before the slab is put in, our electric field naught is just going to be equal to Q divided by epsilon naught times A, which is the area. So in the second figure, with the dielectric in place, we can find that the electric field between the plates and then within the dielectric. So by using the same Gaussian surface. Now the surface encloses two types of charge. It still encloses the charge positive Q on the top plate, but it now is going to enclose the induced charge negative Q on the top face of the electric. So the charge on the conducting plate is said to be free charge because it can move if we change the electric potential of the plate. The induced charge on the surface of the dielectric is not free because it cannot move from that surface. So this is going to be our free charge, right? The charge on the plate. And then our induced charge is going to be the charge on the dielectric. All right, so if we write this out, we get epsilon naught is equal to the integral of E dot dA. So we start with Gauss's law. That's equal to epsilon naught EA. But this time our charge is going to be the difference between the charges. So it's going to be our charge Q minus Q prime, where Q prime is going to be the induced charge on the surface of the dielectric. All right. Therefore, our electric field is now going to be Q minus Q prime divided by epsilon naught A. So the effect of the dielectric is to weaken the original field, E naught, by a factor of kappa. All right, so if I want to, so therefore our electric field is just going to be E naught divided by kappa. So we're going back to our original equation, so that's just going to be kappa times epsilon naught A. Right, so it's the original electric field without the dielectric divided by our kappa constant, right, because it's going to reduce the amount of charge. Okay, so therefore we can write Q minus Q prime, which is the difference, is just going to be Q divided by kappa. All right, so Gauss's law is going to be epsilon naught times the integral of kappa times the electric field dot dA is equal to Q, where Q is just going to be the charge on the plate. So here's our Gauss's law for dielectric. All we're really doing is multiplying your Gauss's law by kappa K. Now we kept K inside the integral because what if kappa changes throughout the dielectric? So it could be a variable, so we're going to leave that inside the integral. Okay. All right, so here we have Gauss's law within the dielectric. A couple things to point out. So the flux integral now involves kappa times the electric field, not just the electric field. The vector is sometimes called the electric displacement d. So this is a new variable, capital D, that we're going to introduce. And really it just means kappa times the electric field. All right, so the above equation can be written as the integral d dot dA is equal to Q. All right, notice that it also involves that epsilon naught. All right, so d is going to be epsilon naught kappa times the electric field. And we're going to call this electric displacement. So the charge Q enclosed by the Gaussian surface is now taken to be the free charge only. And the induced charge is deliberately ignored on the right side of the above equation, having been taken fully into account by introducing the dielectric constant kappa on the left side. Right, so notice that we just have this Q now. We don't need to worry about what the induced charge is because it's taken care of in this kappa term right there. All right, and epsilon naught gets replaced by kappa epsilon naught. We keep kappa inside the integral of the above equation because it allows for cases in which kappa is not constant throughout the entire Gaussian surface, like I mentioned previously. All right, so let's do an example. All right, so this is a dielectric partially filling a gap in a capacitor. So it's not the entire gap, it's just part of the gap. So the figure shows a parallel plate capacitor of area A and plate separation D. The potential difference, V naught, is applied between the plates by connecting a battery between them. The battery is then disconnected and a dielectric slab of thickness B and dielectric constant kappa is placed between the plates as shown. All right, so it's giving you the area, D, your initial voltage, B, which is the thickness of the dielectric, and then your kappa, which is the dielectric constant. All right, so first, what is the capacitance C naught before the dielectric constant is inserted? All right, so our C naught is just going to be given by our equation for a parallel plate capacitor, so that's epsilon naught A divided by D. That'll just be equal to 8.85 times 10 to the negative 12 farad divided by meters. And that's multiplied by the area, which is going to be 115 times 10 to the negative 4 square meters. And this is divided by our distance, which is 1.4 times 10 to the negative 2 meters. We solve that out. You see that our capacitance is equal to 8.21 times 10 to the negative 12 farads, or about 702 picofarads. Oh, excuse me. Let's try that again. Or 8.21 picofarads. There we go. Okay. All right, so what free charge appears on the plates? All right, so now we're solving for Q. We know the capacitance, we know the original voltage, so we can just use our equation. Q is equal to C naught V. And that is going to be the capacitance that we just solved for, so 8.21 times 10 to the negative 12 farads times 85.5 volts. Oops. 85.5 volts. Right. That's going to equal 7.02 times 10 to the negative 10 coulombs, or approximately 702 picocoulombs. All right. So what is the electric field E naught in the gaps between the plates and the dielectric slab? All right, so now we're trying to find what the electric field is between the plates and the slab. So in this region right here is what we're trying to find the electric field. All right. So the surface passes through the gap, and so it encloses only the free charge on the upper capacitor plate. Right. So if we do a Gaussian surface here, it's only encompassing the free charge on the plate. Electric field pierces only the bottom of the Gaussian surface because there the area vector is dA, and the field vector is E naught, are both directed downward. So dA is going to be in this direction, away from the surface. And since it's a positive charge up here, the electric field is also in this direction. There's no electric field going through this surface because it's inside of a conductor. Right, so there's no electric field inside the conductor. All right, so the dot product, so we just have E naught times dA. Dot product of this is just going to be E naught dA cosine theta. Right? And since they're both going in the same direction, the angle between them is 0, so the cosine of 0 is just 1. All right, so all we're left with is E naught dA. So then this equation is going to come, if we put it into Gauss's law, we have epsilon naught times kappa E naught times the integral of dA. Right? And that's just going to be equal to our enclosed charge, Q. Now if we do the integration, we just get A for the area. Right? So this is just going to be epsilon naught times kappa E naught times A is equal to Q. Therefore, when I solve for our electric field is just going to be Q divided by epsilon naught kappa times A. Okay. Well, now we must put a kappa of 1 in here because the Gaussian surface, this first one, doesn't pass through the dielectric. Thus, there's going to be no dielectric constant that we need to worry about. So if we just make it 1, our result ends up being, so we get E naught is equal to Q divided by epsilon naught. This is just rewriting the equation. Plugging in values, 7.02 times 10, what was that, to the negative 10 coulombs, divided by 8.85 times 10 to the negative 12 farads per meter, times 1 for our dielectric constant, times 115 times 10 to the negative 4 meters squared as for the area. And we get an answer of 6,900 volts per meter. Now, note that the value of E naught does not change when the slab is introduced because the amount of charge enclosed by this Gaussian surface does not change. All right, so this electric field is going to be the same whether the slab was there or not. All right, so continuing on with this example. So what's the electric field E1 in the dielectric slab? So if we're trying to find the electric field inside the slab now, we're going to want to use this lower Gaussian surface that we created here, the second one. So what's the electric field E1 in the dielectric slab? The surface encloses the free charge negative Q and the induced charge positive Q prime. But we can ignore the latter because when we use the equation, all right, we're going to use the kappa to worry about whatever the induced charge is. All right, so we don't have to worry about it necessarily. All right, so we're going to go ahead and plug in epsilon naught is equal to the integral of kappa E1 this time dot dA. And that's just going to be equal to negative kappa E1 times the area, which is equal to negative Q. Rearranging this and solving for our electric field. Actually, let's do that down there. All right, so first, let's say the first minus sign in this equation comes from the dot product E1 dot dA along the top of the Gaussian surface. So this ends up being, you end up getting a negative sign because the surface is going opposite of the electric field. All right, and so it's directed, so now that the electric field E1 is directed downward, so this is the direction of the electric field going towards the negative, and the area vector dA always points outward from the interior of a closed Gaussian surface, so that's going to be directed upwards. Right, so this is going outward from the interior of the surface, so that's going in that direction. All right, so you get this 180 degrees between the vectors, and the dot product is negative. This other negative, of course, comes from the negative charge for the enclosed charge. All right, so now that we know that our kappa is 2.61, this equation is going to give us, let's see, going back, rewriting, it's going to be Q divided by epsilon naught kappa times A. That's just going to be our original electric field divided by kappa. So that's going to be 6.90 kilovolts. Oops. So it's kilovolts per meter divided by our dielectric constant, 2.61. So we get E1 is equal to 2.64 kilovolts a meter. So what is the potential difference V between the plates after the slab has been introduced? So what is this voltage change that we're seeing because of the slab? All right, so within the dielectric, the path length is B, and the electric field is E1. And this is inside this dielectric. So within the two gaps above and below the dielectric, the total path length is just going to be D minus B, right? Because the dielectric is just this B. So this D minus B is going to be the area in between the two plates, or the distance between the two plates, where the electric field is just E naught. All right, therefore, our equation for voltage, which is V is equal to the integral from negative to positive E ds, is just going to be E naught, which is our the original electric field, D minus B plus E1 times B. Right, so it's the electric field, it's the contribution of the electric field, or the electric potential in the dielectric slab, which is given by that, and the potential not in the slab, so in between these spaces. And that's covered, and that's shown by this distance, right? The original electric field times the distance between the slabs. Okay? So plugging all of this in. So we get 9,600 volts per meter times our distances, so 0.124 meters minus 0.0078 meters plus the electric field inside the slab, which is 2640 volts per meter times 0.0078 meters. And this gets us a value of 52.3 volts. All right, so you can see that we went from an original voltage of 85.5 down to a voltage of 52.3 after you introduced the dielectric slab. So this is less than the original potential difference, right, of 85.5. What is the capacitor with the slab in place between the plates of the capacitor? Or what is the capacitance with the slab in place between the plates of the capacitor? So what is this change in capacitance? And we see that the capacitance is now 7.02 times 10 to the negative 10 coulombs, which is our charge, divided by 52.3, which is our new voltage. You can see that our capacitance is 1.34 times 10 to the negative 11 farads, or approximately 13.4 picofarads. All right, so there's our answer for capacitance. Let's look back to see what our original capacitance was. All right, so we found that our original capacitance was about 8.21 picofarads. With the dielectric, it goes up to about 13.4 picofarads. All right, that's it for the chapter. We'll see you next time.